So the first question is that why do we have probability density on the y-axis of PDF? And when we hit enter, you will see that we have the plot for the normal distribution, right? I'll uncomment the histogram also, and you will see that it is approximately similar to the normal distribution. And when I make it 0.1, you will see that it has very less spikes. And so now we can say that it is neither under smooth nor over smooth. And this is what we require. Hello friends, welcome back to day 41 of the 100 days of hell with Python algo trading. Previously, we have learned about the probability distributions, in which we have learned about the PMF, that is probability mass function, and PDF, that is probability density function. And also in that session, we have understood that how to calculate CDF, cumulative distribution function of PMF and PDF. And after that, we had one question, that why we have density on the y-axis of PDF. Because in PMF we had probability on the y-axis, but on PDF we have probability density. So in order to answer that question, we will understand that how it happens in this session, right? Why do we have the density and how do we calculate the density? So without further ado, let's get started. So the first question is that why do we have probability density on the y-axis of PDF? Because in PMF we have discrete random variables. And it's very easy to calculate the probability of the discrete variables. But on the other hand, in PDF, we have continuous variables. And it becomes difficult because we have infinite data there. So we cannot just directly calculate the probability in that data. So we calculate the density. And now we will understand that how do we calculate the density. So for that, we have a method known as the density estimation, right? So let's understand that. So, density estimation is a statistical technique used to estimate the probability density function of a random variable based on observed data. So now, to estimate the density, we have two methods. First is parametric density estimation and second is non-parametric density estimation. So in parametric, it assumes the data follows a known distribution with fixed parameters, example, normal or exponential. Let me show you what are some common known distributions. So, you can see here, so the first is normal distribution, which is also known as the quotient distribution. And in that, you can see the formula to calculate the PDF and to calculate the CDF, right? So to calculate the PDF and CDF, we just need to find the mu, which is the mean of the distribution, and the sigma, which is the standard deviation of the distribution. And once we are able to find the mean and the standard deviation, it becomes so easy to calculate the normal distribution, right? We also have another known distribution, which is the exponential distribution, and in that you have to find the parameter lambda, which is the rate parameter. So these are the parameters we are talking about, right? So once we are able to calculate the parameters, so it becomes easier to estimate the density. We also have binomial distribution. You can see the formula, and for all those, let me show you, like this is the normal distribution and this is the graph for the PDF and CDF for the normal distribution. Again, this one is the exponential distribution, and in this we have to find the parameter lambda, and you can see the graph for that also, right? Again, you have binomial distribution. In that you have to find the n, the number of trials, and the p, which is the probability of the success in a single trial, and you can see the graph for that, right? And also we have the uniform distribution. In that we have a and b, the lower bound and the upper bound, and you can see the graph, which is very straightforward for the uniform distribution. And another known distribution is the Poisson distribution, in which you have to find the lambda, which is the average rate of occurrence, and this one is the graph for the Poisson distribution, right? So what we'll do, let's say we have data. So first we'll plot the histogram, and we will try to compare that with the existing known distributions, and if it matches to any one of them, and then we will calculate the parameters, and with the help of those parameters we'll be able to estimate the density with the help of the formulas, which is the PDF and the CDF, right? We have seen that these are the parameters and this is the formula for PMF and CDF, right? You can see here the parameter and the formula, the parameter and the formula, the parameter and the formula, and again the parameter and the formula. So in parametric, we try to compare with the existing distribution and we try to estimate the density, right? On the other hand, we have the non-parametric density estimation, in that it makes fewer assumptions about the data's distribution and is more flexible. Example, histogram and KDE, kernel density estimation. So in non-parametric, we do not assume it to any known distribution, and because of that, it becomes so flexible. Now let's take an example of parametric density estimation. So let's proceed. For the definitions and the formulas and the graphs, you can refer the GitHub. I'll push all these things to the GitHub and you can refer that. Okay, so now let's understand the example of parametric density estimation. So what I did here, I have some random data in which we have random dates and prices. And for that, we have calculated the daily returns. So you can see here the returns, and with the help of percentage change and drop NA, let me show you the returns here. So you can see here the returns, and these are the returns, right? 400 days. Now what we do, like this is the random data, but you can take it for any data, right? You have a data. What you will do, you will first directly go and plot the histogram. So let me plot that. And you can see here, now you will try to compare that whether it is somewhat looking like any existing known distribution. If it is looking like that, then you will direct all your calculations towards that particular known distribution, right? So if you see here, it is somewhat looking like the normal distribution, right? So now what we'll do, we know that in normal distribution, first we have to find the mean and then the standard deviation, right? So we'll proceed further and we'll try to find the mu and sigma. We know that that is mean and standard deviation, right? So when we find that and when we try to print, let me show you, this is the let me first comment this out. So you can see here, this is the mu, which is mean, and this is the standard deviation, sigma, right? Okay, now what we'll do, we will try to plot the parametric density estimate. As we know that it is somewhat looking like normal distribution. So we have already calculated the mu and the standard deviation. Now as we already have the mu and sigma, so what I will do, I'll generate the values for x-axis, right? And then I will try to plot on the normal distribution. You can see here in the SkyPy, we have this normal.pdf, and inside that we can pass the value of x, then the value of mean and the value of standard deviation, right? And when we hit enter, you will see that we have the plot for the normal distribution, right? Now I'll uncomment the histogram also, and you will see that it is approximately similar to the normal distribution. And this is how we can estimate the parametric density, right? So it depends actually. So I have shown you multiple distributions here, and if your data distribution is somewhat similar to these, then you will try to estimate with the help of these already known formulas, right? But what happens when it doesn't match to any distribution, any known distribution? So in that case, you will follow the non-parametric density estimation, right? So what is non-parametric? It makes fewer assumptions about data's distribution and is more flexible, right? That is KDE, kernel density estimation, and this is very, very important. So now we will understand this. Okay, so now let's try to understand the non-parametric density estimation. So in parametric, we use the existing known distributions, and in non-parametric, we'll not assume any existing known distribution. Okay, so let's understand that. Non-parametric density estimation methods are used to estimate the probability density function of a random variable without assuming a specific parametric form for the underlying distribution, right? They are more flexible than parametric methods, which assume the data follows a known distribution with a fixed number of parameters. In parametric, we already assume that there are only a fixed number of parameters, and based on that, we were calculating the density estimation. But in non-parametric, we do not assume any of that. So let's take some examples of non-parametric. So the first and simplest example is histogram. Then we have KDE, which is the most important. Like we will be using this 90% of the time. And we also have the nearest neighbor density estimation. Now let's understand some pros and cons of the non-parametric density estimation. So the pros are flexibility. Means non-parametric methods do not assume a specific function for this distribution, making them highly adaptable to various data shapes and structures, right? Because in reality, we'll not be having any fixed shape, right? On base of data, it can be various number of shapes, and that's why it becomes so flexible. Then applicability. they can be applied to a wide range of data types and distributions without needing prior knowledge about the underlying distribution. Then, data-driven. These methods rely directly on the observed data, providing a more accurate representation of the data's characteristics, especially for the complex or multimodal distributions. We will understand them shortly, don't worry. Now we have few cons. The first is computational complexity. Non-parametric methods can be computationally intensive, especially for large data sets, as they often require more processing to compute density estimates. Then the second is parameter sensitivity. The performance of methods like KDE heavily depends on the choice of parameters such as the bandwidth, and poor parameter choices can lead to a oversmoothing or undersmoothing. We will just understand these also. Next, the boundary issues. Non-parametric estimators can perform poorly at the boundaries of the data range, leading to a biased density estimates near the edges. So that's also the issue of boundary. Okay, now let me tell you with the help of an example. So we have this example here, and as I have already explained you that when we have, let's say currently the bandwidth is 0.1. So if I change it to 1, what will happen? You will see that it is over smooth, which is not required. And let me make it 0.001, and what will happen? You can see the spikes, a lot of spikes. This is also not required, right? Let me make it 0.01, and you will see that we still have the spikes, and which is also not required. And when I make it 0.1, you will see that it has very less spikes, and so now we can say that it is neither under smooth nor over smooth, and this is what we required. So that's the estimation of the density, right, with the help of KDE. So we will understand this in detail in further lectures. It was like just a basic overview of this, and whenever we require this more, we will try to understand it more deeply. Okay, now let's move to the notepad and try to understand the formula for KDE, kernel density estimation, and try to understand this more intuitively, right? So the KDE stands for kernel density estimation. It says it uses the kernel function to smooth the data and create a continuous estimate of the density, right? And the formula is fx equals to 1 upon nh, summation of I equals to 1 to n, and k in bracket we have x minus xi upon h, in which k is the kernel function, let's say the Gaussian, or we can say the normal distribution. Then h is the bandwidth, which I have shown you recently that so when we increase and decrease the bandwidth, it affects the smoothness of the distribution, right? It becomes over smooth or it becomes the under smooth. Let me again show you. So what I will do, so currently it is normal smoothing, say the bandwidth was 0.1, and let me make it 1. So if I make it 1, you will see that it is over smooth, which is really not required, right? And if I make it 0.01, you will see that there are multiple spikes, and it is known as the under smoothing, and it is also not required. So we need to have the balanced parameters. So I will just remove it again, and I'll make it 0.1, which is the normal smoothing, right? Now, n is the number of data points, so it depends on your data. So like generally we do it for the sample data, and we try to estimate the probability density of the large population, right, based on the sample data. So this was it for this session for the KDE, or we can say the parametric and non-parametric density estimations. I know we haven't gone very deep into this topic because I know that at this stage we are at very basic concepts. So once we are done with all the topics, we will again cover the important ones, that is the KDE and the rest of the remaining important topics. And as along with the learning, whenever we require any topic, we will again go through that quickly. Okay, now let's take another example of kernel density estimation to estimate the volatility of the stock prices. So we'll try to estimate the volatility, and we know that it is very crucial in the risk management, in the option pricing, and we know that it is very crucial in the risk management, option pricing, and the portfolio optimization, right? So let's understand that, and here also we will create the synthetic data. So here we are trying to simulate the intraday prices for the 20 trading days with 390 minutes per day trading, right? And then we are trying to calculate the intraday returns. And you can see here that these are calculated as the percentage change in price from 1 minute to the next. So the PCT change function in pandas compute this, and the drop NA removes any missing values. Okay, so let me first show you the price series. So you can see here This one is the price series. And then we have intraday returns. So that also I'll show you. You can see here. These are the intraday returns. Some are negative, some are positive. After that, what we'll do, then we will estimate the density using KDE, right? You can see here, uncomment this. And then we'll plot all the values. I'll just uncomment this quickly. And let me run this. So you will see that we have kernel density estimation of the intraday returns, right? And here, if you change the bandwidth again, let me show you. Let's say if we make it from 0.5 to 0. Let's say 1, you will see that we have more spikes, right? Again, if I make it from 0.01 to 0.1, you will have a smoothened curve, right? And if you make it from 0.1 to 1, you will see that it is completely smoothened and it is covering a wide range, which is really not required. So we have to have a good estimation. So I'll again make the bandwidth as 0.05, and it is somewhat like expected. It is somewhat normal, and it is what we require, right? Sometime. So you can use this KDE in various applications. It's completely up to you that how much you can think and use this KDE. This is really very good non-parametric estimation technique, and it is widely used, right? You will be using this a lot in the future. We will also try to understand this in future again when we require it, and we'll try to learn about it more along the way whenever you require, right? So today we try to understand the parametric and non-parametric density estimation techniques, and in the next we will start with the probability distributions, and after that we will learn more interesting topics along the way. And you can also let me know that what kind of topics you want to learn, and we can start with that, right? So that's it for the day. I'll see you in the next video. Until then, bye bye, take care, have a nice day.